So next up, we have Jacob Nordin, all the way from Germany, to tell us about AMPEL.
Is this thing on now? Yes. Yeah. Okay, hi everyone, I'm Jacob Nordin. I'm going to talk about the AMPEL analysis engine. Thanks for inviting me here. It's a very nice meeting so many of you again. I think I talked to most of you. If you haven't talked to me, I think the best part is if I can get to talk to you in the breaks. I'm not going to do the live demo because we have so little time and because we didn't get so many alerts last night, so I didn't think it would be fun. Instead, since they were short, I wanted to communicate a few key messages that I hope you can bring with you. So kind of one of the first questions that we get is, how do I get data? So I'm going to mention the easiest way to get AMPEL by Rubin alerts. And this is to dial into one of our curated Kafka streams of Rubin alerts. And the easiest one to do that is to use the Hopscotch SIMA service. So I think a fair amount of you probably knows this. But this is, everyone can get an account there. You log in. There are a number of topics. I see Gautam taking photos. I think he might speak more about this later. So go there, explore it, get an account, and then there will be different topics. And then I'm going to mention 3 different topics to you now. We might have more, but these are the ones I mentioned now. Extragalactic transients. So these are Rubin alerts that we believe are highly likely to be extragalactic transients, probably because of their photometric classification or because of their distance estimates. Extragalactic infant are for those of you who want to use the Rubin depth to discover very, very young transients. So these are likely going to be associated with nearby galaxies. And then we have TO transients, also pretty clear what that is. So these are alerts that have been associated with one or another multi-messenger signature. So probably a LIGO alert or an ice cube neutrino alert. And these could have triggered T observations from Rubin, but they might also not. So depending on what you're interested in, these are, I think, 3 good topics to listen to. They are all designed to have at least initially, very small throughput rate. So it shouldn't be any problem to do this locally on your laptop. So what will you get when you do so? Well, you get a bunch of Python objects that contain information. And I mean, you can just look at them and see how they're defined. But there's also a little Python library you can use to parse through these alerts, and it actually keeps track of them for you, stores them locally, and so on. And that also allows you to visualize them, to filter. We'll also add photometry from other surveys when it's available. Eventually, I imagine you will want to automatically parse these reports somehow. I mean, they are very simple objects. So this was my first message. If you want to get these in the beginning, we will keep these streams very conservative. Gradually, we'll add more data to them. But this is a good way to get data. OK. The second thing I want to communicate is what is it we are adding to these curated alert streams. And that's mainly 2 things, photometric classification and catalog information. Also pretty standard things, but I wanted to highlight some words of caution. So we are trying to be very carefully about versioning and verification of the models that we're using here. So basically, to the left, we have a series of models that have been trained on real ZTF data. So that's anything that contains a noise ZTF tag. And so this is some recent studies we've done. And there we've really seen that anything that have been trained on real data with distributions that match your target sample performs much, much better than your other data sets. And this is something I think we'll see for Rubin. It's no surprise in that. We'll have to wait a year until we have retrained classifiers. We will also have a set of other classifiers trained on synthetic data. And here we're focusing on classifiers that were used in blinded challenges. So either the elastic general challenge, so this is, you can't read anything, but this is one of our models that performed well, or blinded models that were run, that were used in the Malone TD challenge. So these might be also two tags that you're seeing. So one thing I want to highlight, use these are the highest quality photometric classifiers, the most well-studied we found, but they still come, and we're trying to quantify their uncertainties, but they still have uncertainties. The other thing we are including is catalog information. So distance, the way we're doing this is that we're collecting all the catalog information we have, all the distance information, and then we're organizing that based on how good the redshifts typically are. And so here you can see, so we've tested them. Again, I like to test things with real data. So we've taken a lot of real transients and we've compared how good different catalogs actually are at predicting the distances. And you can see that there are some wide bumps. And there's no surprise that catalogs that use photometric redshifts perform a lot worse. So what we've done is that we've grouped catalogs in different groupings with different integers. So basically, with each of the reports, you will get both a distance and a group number. And this group number specifies what quality you have of the redshift. So for example, if you're using anything from above group 3, you're probably using photometric redshifts. And this is something you should know. OK, so those were some kind of general information. The third thing I want to say is to talk a little bit about this concept of AMPEL as an analysis engine. So as you'll see, I will not show you a front end to access the data because that's not how we operate. So I'm going to take a half a step back and talk about the science goals that led us to start developing AMPEL. And there are some examples. So one has to do with doing cosmology with type 1a supernovae. So this is from one of our latest collection of type 1a supernovae from ZTF. The Roman predictions were very impressive with tens of thousands supernovae, but we actually already have that now, ZTF. The problem there is that we don't only need to have the supernova, we need to know the selection function very, very well. Second example have to do with multi-messenger studies. So we can hope to find another 170817, but we most likely won't, or maybe we won't. But what we'd rather find will be a whole bunch of potential multi-messenger maps, and we'll find a whole bunch of optical transients with sparse information, and we'll have a whole bunch of potential source models. And we somehow have to compare that to ideally confirm source models or rule them out. And a third thing that is happening now, and that's a lot of fun, is this automatic triggering of telescope networks. So these are very different science goals, but what they have in common is that they are in some sense inherently statistical. We're dealing with large samples that we're somehow evaluating, and we're studying in performance metrics. So these were the kind of studies that we were thinking about with these very large samples we have. So the kind of questions that we get there is, will this analysis that I'm doing now, will we be able to reproduce that in 3 years? Can I improve on a pipeline that some other grad student wrote 5 years ago without having to redo everything from scratch? Can I rerun all of the old data with this new improved method that I have and compare my performance compared with the old one and understand what objects I would have targeted then that I won't? So we try to develop something that can answer these questions. So the idea then of AMPEL as an analysis engine is that how we will be working with these large data set works a little bit like a cycle. You have an idea, you implement that as an algorithm. Once that you have that, you process data, you evaluate the data somehow, you improve your ID, and then you get to improve your algorithm, and then you go around here. And possibly in each cycle, you change what sort of data input you're having, from simulated data to archive data, and then eventually to real-time data. And then once you have real-time data, having front end and doing visual confirmation is critical, but it was never the key point of this process for us, and we typically use other brokers for that. So AMPEL, in essence, is an engine that can carry out these studies in a way that guarantees provenance and reproducibility. So the development process, very shortly, You first install AMPEL with all the bells and whistles locally, and you develop some sort of core analysis schema using modular units. Most of them will be existing. And then you run it yourself. To get back to the question from the last session, we would do it. You would have a big bunch of alert torrents that you would run locally and reprocess until you recreate the selection function that you want to have. And then eventually, when you're happy, you upload it to a computer center where you run it on say, a full archive, or you implement it in the live processing. That's certainly possible as well. And so if you want to go ahead, you can exactly reproduce the classifications we're doing right now for Rubin alerts. So you can go to one of our GitHub repositories, clone the repository we have there, install it, and then run one of our jobs that will then, on sample alerts, carry out exactly the classifier with the version that we have locally. Okay, so some of my conclusions. AMPEL, in a word, it's implementing code to data and astronomy. We have some curated set of Kafka streams that, for most users, will provide high quality alerts, and I encourage you to use them together with what other input sources you have. These alerts have augmented information for photometric redshift classifications. These will be critical to use Rubin data. Just use them with caution. And if you now or in a few years realize that you have a large sample, you start thinking of provenance, reproducibility, scalability, then just think of running AMPEL yourself. There are some links there. Otherwise, come talk to me. Thank you.
All right, questions? Gautam.
Hey, Jacob, this is very cool, particularly the repeatable, scalable aspect of being able to redo the entire analysis. For a lot of the science cases, I can imagine people will want more data that is than in the Rubin alerts, external catalogs, maybe cross matches with some service like IceCube or LBK. How does this infrastructure work when that data itself may not be public, or that data may not be itself readily available?
There are different levels to that. So this is all modular. So for example, we have a lot of IceCube users that then can download IceCube alerts, and some of that is private. And so for these, for example, with these jobs that you have, there's a system of where you can provide secret passwords occasionally that are required to run certain units. And I'm trying to minimize that, but yes, there is a system. Some things are hidden behind permissions, but for example, for the public classifiers that we're running, they are fully public.
Right, other questions for Jacob? Honestly, again.
So from the curated Kafka streams, does this mean I can't define my own stream? Like a number of science cases would be useful. Like maybe I care more about sky localization and maybe I want to go down to limit my alerts and maybe a lower signal noise or something like that.
You can, absolutely. I mean, this is where you then start by actually downloading AMPEL yourself. And then you get, basically for every day, we take a random subsample of all the alerts and publish as a collection that you can just download. Then you process them locally, and we have a filter function that you tweak until you're happy. And when you're happy, you upload that to the live unit, and then you can have that as your own separate stream.
But is that a stream if I'm bulk downloading them?
Well, it's not initially, but once you have tweaked it based on static data and you upload it to the live instance, then you can have what passes your filter in real time distributed as a stream. How we would set it up would depend a little on how many would be using it and what the throughput would be. But that's, I mean, already for some people have basically their own private hopscotch topics being sent out of AMPEL. I'm not so happy about that either, but that is certainly possible to do.
Cool, thanks.
Shreya. Shreya, here in front.
Oh, there.
Thank you for your talk. Could you say a little bit more about what goes into the TO transient stream and how you're filtering on external alerts?
So to some extent, that is still to be defined, right? But there are a few things we will be doing. First, everything that was observed as part of a Rubin TO observation that passes some minimal quality thresholds will be sent to that topic. And then also when there are basically when the multi-messenger groups, they do specific matching to say another LIGO map to see whether there are coincidental matching. Then whatever is found in that matching is also sent to that topic. But that's not a matching that I do. That depends, for example, if the what the IceCube group do. If they do that, then those alerts will also come there. So that exactly what comes out in the end will a little bit depend on what the community do.
Great, thank you.
Awesome, thank you. Let's thank Jacob again.